Bonjour, my name is Eli. I work at Google, where I lead the security and anti-abuse research team. And today, I would like to talk about deep cryptanalysis, which is the idea of applying deep learning for cryptanalysis, and more precisely delve into the question of whether it's going to be a revolution or if it's going to be a fashion which is going to go out of style in the next few years. Before getting started, let me mention that the slides you're about to see are available on my website, and you can download them if you'd like to follow along, or if you would like them to review them after the talk. With this out of the way, let's get started. AI is revolutionizing the world as we know, and many applications are surfacing which are going to change drastically how we live. For example, self-driving car is going to change how cars are going to be used. For example, reducing the need of parking in the center of the cities, or allowing people with disability, such as being blind, to be able to drive to places without the need to rely on other human beings. And I'm really excited about AI progress, but what it has to do with crypto and more precisely cryptanalysis research. My thesis is that over the last few years, we have seen many breakthroughs across many fields being done by leveraging AI advance in agents field. For example, very recently, August 2021, at the time of the recording of this video, DeepMind announced the release of AlphaFold 2, which essentially is able to solve the protein folding problem. So protein folding problem is this need to predict how a protein is going to fold in 3D, so we can understand how this protein will interact with other protein and understand how it is going to affect many of the biological system of the body. And as you can see on the left side of the slide, the progress due to deep learning in the last few years, from 2018 and 2020, have been incredible. And they reach a point where now they're able to solve this protein folding problem to atomic precision, which is a holy grail of the field, and essentially solving it and subsuming every existing technique which did exist before, as the need to doing crystallography or those complex techniques are completely unnecessary, as we're able to accurately predict what is going to be the 3D shape of the protein. And the way they are doing this is by leveraging a lot of innovation from adjacent field, including NLP and attention mechanism developed there, to be able to increase drastically the accuracy of their model. And this is my thesis today, which is we might borrow from some of the advances in AI and apply them to cryptanalysis. So if we have this idea of there are a lot of things in AI that have been surfaced in the last few years, which are very powerful and are very successful in many fields, then the question becomes, okay, how can we do that the most efficient way? Where are the areas we can apply those techniques and get the most benefit and the most progress for the field of cryptanalysis? So to answer that question, today I'm going to cover 4 points. I'm going to actually try to answer that question. I don't have all the answer, but at least I'm hoping to give you some pointer and some idea of where it might go. So the first thing we're going to cover is how deep learning can directly improve existing use cases. Equally importantly, we're going to talk about where deep learning, I think, is not going to be a good fit, and applying it might not yield good result and potentially are not areas that should be invested too much in. Then we're going to talk about the thing I'm the most excited personally, which is how can we use deep learning to unlock new use cases, doing things we were never be able to do before, and how the direction we can go to try to do this. And last but not least, I would like to reflect on how we can use the entire ecosystem of deep learning, not only learning models, but also all the tools such as explainability, hardware, libraries that have been developed to push further the field of cryptanalysis. Before getting started, just a word of disclaimer. The slides you're about to see are very high level, and I'm glossing over a lot of detail, including a lot of the difficulty to apply deep learning for cryptanalysis, and it might at time seems easy. However, the field is very nascent and it's not that easy. There is a lot of failure, there is a lot of learning on how to best do things. I'm expecting this to get easier as time passes and the field is figured out, but this is a very researchy field. So there's a lot of impact to be had, there's also a lot of difficulty to overcome, obviously. So please keep that in mind as we go through the slide. Okay, let's get started with improving existing use cases. The first question we need to ask ourselves is, what makes a good target? So the first thing you absolutely need, or you really need, is the ability to collect a lot of data, because deep learning by nature scales with data. The more data you have, the better your algorithm will be, the better your result will be. So a data-rich use case is usually what you're looking for. Second, the problem has to have a lot of structure and to be differentiable, or at least somewhat differentiable, so we have a way to guide the descent, the gradient descent. Some problems in cryptography are not differentiable, and those, as we're going to see further in the talk, are not necessarily the good fit for the machine learning. They might probably work a little bit, but that's not going to give you the result you hope. And last but not least, deep learning really shines when it's about to build a statistical model, to learn a statistical model, essentially. So anything where we know there is a biases and we would like to exploit it better or start to exploiting is a good target. Case to the point, side channel attack are very, very good example of where you can apply deep learning. And that's something our team have been doing for many, many years now. And we call that side channel attack automated with machine learning, also known as camel. And I'm going to briefly cover how they work. So hopefully that gives you a sense of how you can successfully apply deep learning to existing use cases and get better result. So the reason why deep learning is really good for side channel attack is because in a way it is a template attack, which was previous state of the art on steroid. What I mean by that is deep learning alleviates a lot of the difficulty of previous state of the art. Most notably, deep learning is able to do not require to pre-process the traces collected as part of the side channel attack. What I mean by that is usually when you have a template attack, you need to make sure all your traces are all perfectly aligned, and you need to select which windows inside it you're going to use to perform your attack. Deep learning, due to the ability to be invariant to translation to a certain extent, only allow you to just work directly on the trace. And again, this is this idea of emulating previous field. In computer vision, they started to have a lot of features like SIFT and so Smurf and so forth. And as time passed, they realized that the best way to use deep learning is to work on raw pixels, right? And most all of the algorithms these days literally work pixel by pixel, and they feed as much of raw data to the machine learning to not introduce biases, unnecessary biases. So similarly here, for deep learning, for cryptanalysis, it seems logical to go back and feed the raw traces and let the machine learning learn its own thing, rather than to introduce a biases by the human deciding what part of the trace should be done. Then, in a similar vein, a lot of the attack in side channel attack use a statistical model. For example, for AES side channel attack, we use the Hamming model, which is an approximation of what is the distribution of the weight should be. Because the machine learning is going to learn its own representation, introducing an approximate model is detrimental to the learning, so you don't have to have this kind of approximate model, which also reduces the complexity of the human intervention. Third, deep learning is really, really good at providing ways to perform efficient probabilistic attack and helping to finish the attack with a brute force step if need to be, because it's going to output pseudo-random probability, which allow you to know which byte value you should target next. And last but not least, because deep learning has this ability to report metric during training, it is very easy to follow along how well the attack is going and how much more it can increase, right? You can see the slope and so forth. So those are kind of the 4 reasons why deep learning is a very, very good fit for a side channel attack and why I'm expecting it to be the dominant technique in the next few years. It is also very important to mention at that point that the core power of deep learning is deep learning scale with data and compute, which means that if you have a statistical biases and then it's not giving you enough result, you can almost linearly improve the quality of your result by adding more data, making your model bigger and training for longer. And there is some ratio to that, and the best paper I know of that is from natural language processing from OpenAI, which is scaling the law of neural language models. And this paper shows very clearly that deep learning scale linearly to up to how much we can go, from 1 million parameters to billions of parameters. As long as you feed enough data and you have the right amount of compute and the right size of model, deep learning scale almost, as far as we can tell, infinitely. And this is what really separates deep learning from other previous technique, which is it doesn't stop. There is no scene limit just yet of how far you can push it. And that is very exciting because it means that even protected implementation, which today are hard to do, tomorrow with enough larger model, enough compute and enough data, will be able to probably attack them. It also means that deep learning is going to tilt heavily cryptanalysis and crypto in the favor, at least for side channel attack, in the favor of the attacker, because this is a very powerful tool and we'll have to find different ways to develop countermeasure which will be efficient against those very, very more powerful attacks. If you're interested in learning all the detail on how deep learning based cryptanalysis, side channel attack are working, I wrote a very long tutorial, a very detailed tutorial, which covers all the concept and give you code to run it. You can find it on my website at the address you can see on the slide. We're also hoping to do a paper with way more data set and a way more formal treatment. Sadly, this paper is delayed due to the pandemic. We cannot enter our lab, so we cannot finish the experiment. Hopefully, as the pandemic subsides, I will be able to release it. I'm afraid to give any timeline because I don't know when, but hopefully at some point we should also be able to provide a lot of different type of data set and models so you can get started and have all the necessary components to enter the field in an easier way. Today, to illustrate how that works very briefly, I'm going to tell you how you can apply deep learning for side channel attack, and more precisely how to attack a SMT32F4 on which TinyAS, which is a completely unprotected C++ implementation, is running with the goal of recovering the key. And the side channel attack for deep learning is very similar to traditional side channel attack. You do the encryption, and as the encryption is performed, you collect the signal, and then that's where it's a little bit different. You pass the recorded traces to the deep learning network, and the deep learning network will output prediction, and you combine them, and you repeat the encryption multiple times. And ultimately, when you have enough of those, you can confidently recover the AES key based on those predictions. AES has multiple attack points, meaning point in the algorithm where the memory is updated, and that create a power change or an EM change. Today we're talking about power. So three main one is the literature as the key is loaded in memory. There is a subbyte in where the key is XORed with a plain text, and then subbyte out, which is when the output of the S box. Generally, we did observe that key is not necessarily a good target because sometimes it doesn't, most of the time it doesn't work. The exception would be if you make a mistake and you include the key scheduling algorithm, which should not be part of the attack, but sometimes if your trace is triggered too early, it might happen. It did happen to us, and then it seemed to work. However, if you focus only on the encryption, which you should, because the key is only loaded once in the real hardware, then the key attack point doesn't seem to work really well. Sub-byte in, sub-byte out usually work, at least on unprotected implementation. They seem to be working equally well. So today we're going to do one of those two. And the model we usually use as a first pass is a hypertune residual convolution neural network. So it's very, very similar to the one used in vision. ResNet is maybe the original architecture you could use as a starting point, and we have hypertuned to decide the number of blocks and size of filters, and this type of model work really, really well. They're also very, very small, about 250k parameters, which is very, very small, run very, very fast, and give us good result. They are not state-of-the-art. You can do way better with additional architectures. However, we tend to use those for unprotected implementation. Very similar to template attack when you run deep learning based side channel attack. You need to have 16 models because you are recovering 1 byte at a time. So to recover the full key, you need to train 16 models, and each of them will predict 1 byte of the key. And then you combine the prediction and get hopefully your key. The way you recover the key from the model is you take a single trace. So I'm going to explain first with a single trace and then explain how you combine them. So you take your single trace, you pass it to the neural network, and the neural network have as output what we call a softmax, which basically ensures that the output, so sum of the output is equal to 1. And so you can treat that as kind of like pseudo probability. And so that would tell you what is the most likely value for the byte you're trying to recover, what is the second most likely, and so forth. This makes it very, very easy to combine traces and increase your confidence and recover your byte by summing the output of multiple prediction on multiple traces up to a certain point. I would note here that for mathematical correctness, you have to sum the log of the probability, the log of the output plus epsilon for numerical precision errors. But case to the point is you sum all your prediction and then you accumulate confidence, and the highest value become what is the model prediction. The second best value will be, well, what you can try with brute forcing and so forth. And that explains why this make it very, very natural to do a probabilistic attack, because you exactly know in a fully ranked order what are the potential value you should try to recover a given byte. So the model we usually have don't reach 100% accuracy. In the tutorial, I think they reach sometimes as low as 30% accuracy. However, even with this low accuracy on the machine learning numbers, they're able to recover 100% of the bytes for tiny errors in at most 4 traces, and most of them, I think 81% is correct, in a single trace, which is as low as you can get. So you get state-of-the-art attack by training a model. That shows you the power of it. It also shows you that there is kind of a disconnect between what the model accuracy is and what the attack accuracy is. So you have to perform the real attack and the real recovery to get a sense of how good is your model. Some models for very protected implementation tend to actually have a much lower accuracy and still with enough traces is able to recover the key. So that's one of the gotcha you have to pay attention to. Equally important, and changing gears, is what would not be suitable cases for deep learning, where we will have bad target and things which might not work as well as side channel attacks or any of those potentially high value usage. So what makes a bad target is the lack of data. Obviously, as I mentioned in the previous one, we need a lot of data. So if you don't have a lot of data, that is very, very difficult, because deep learning, as we saw, feed into having more data to be better. If your problem does not have a lot of structure, meaning that one point in the space is not informative of the other point and they are not continuous, that's going to be really, really difficult, because the model gradient cannot really guide the descent, right? The descent cannot be really guided because there is so much hill and valleys. And Last but not least, there are problems for which we already have very efficient solution, and you can certainly redo it with deep learning, but it's not going to bring any more value, and deep learning is somewhat compute intensive and data intensive, so you're probably going to get a less efficient solution for the problem we already have solved, so probably not the best target. What I mean by the problem need of structure, and I think that's a very important point because probably the point which is the hardest to gauge, is the domain needs to be somewhat smooth. Deep learning usually like when things are continuous and you can go from one point to another, and then the gradient descent slowly approximate what is the lowest point. And that is not the case in many applications of cryptanalysis. For example, one thing to not do would be to try to use deep learning to attack cipher which have repetition of keys. Visionaries come to mind, or any of those. I did actually implement it as a thought experiment and spent a few days in December, I think 2019, doing that. So you can technically make visionaire differentiable and use kind of like a proxymetric, which is reconstruction of the plain text, and you can try to guide the descent that way, and it kind of works. And as you can see on the diagram, it converges, and you will get better, and the distance between your plain text and your expected plain text, I would say, and the one output by the model is going to shrink, so it kind of works. The problem is, it kind of is the word here. It never gets the perfect answer, and it never fully learns exactly what is the output. You can make the model probably bigger, and we probably can get to a point where it memorizes all the combination, and you might be able to get there. But my point was, it doesn't work that well, and there are way better ways to do it and way more efficient ways. So clearly, this type of attack is not what you should use deep learning for. It might work, but it's not going to be competitive, and it's going to be a little bit difficult to carry out and not worth the effort. Let's talk now about the thing I'm the most excited about, and which is, can we unlock new use cases using deep learning? And of course, that's $1 million question, right? Which is, if there is an application of deep learning for cryptanalysis which have never been found, then it's a breakthrough. So where those breakthroughs might come from? I don't have the answer, but I do have some idea of most likely places where if we dig enough into, we might find it. The main driving thought I have there is that if there is an underlying structure and we can't easily express it with current tool, whether it's formally, whether it's with equation, whether it is with statistical analysis, then we might be able to use deep learning to approximate it, and this approximation will be good enough that we'll be able to succeed where we never succeed before. Example of this line of thought would be the idea of trying to attack large CPUs, which have enclaves and are doing computation, and those are really hard to attack with side channel attacks because there's a lot of noise. There's a lot of other components into the chip which actually are polluting the signal, and that's not doable with current techniques. By applying side channel attack, it might be possible to do it, and that's something I'm really looking forward to try at some point. The other places where there might be a lot of opportunities, and that's the one I'm personally the most excited about as I'm working on self-supervised learning for other reasons, is this idea to learn without label. And this is clearly something you cannot do today. Today, we need to have, with current techniques, some idea of what the labels are. Deep learning has spent a lot of time in the last few years to actually try to answer this question of, can we learn some representation of the space without having kind of explicitly say what each image is, and that's self-supervised. So the reason why this is interesting for us is because if we're able to adapt those techniques, then we're able to perform black box attack. Not only now chosen text and chosen cipher, now chosen text will do. And this is a big step forward, at least for side channel attacks. So how that would work is basically you would look at how the model learned, and from what it learned or how the output is, you might get a guess of what the bytes of the key is. So there's two recent papers who attempted to do that in two different ways, and they are both very, very interesting to read, and I encourage you, if you're interested, to delve into those. The most recent one is called Skull, where the idea is they try to do clusters, and they are trying to find the places where the cluster is the tightest. And this is most likely where the correct key is. The previous one is called non-profile deep learning based side-channel attack. And the idea is you try to train models on every possible byte value, and you look at the one who converge the best. And the idea here is, with the right formatting and so forth, is the idea is that the only one who can really converge is the one which has the true key, because the rest is going to learn noise. And it seems to work really well. So those are kind of two initial ideas on the space, and they seem very promising. So there is definitely something there. Last but not least, let's talk about what I call spatial tactic, which is this idea of using some of the deep learning tools to help us do cryptanalysis. And repurposing those deep learning tools might help us in ways which are kind of unexpected. What I want to show you here as an example of that is something we've been able to do, and we're actively researching, which is this idea of building a side-channel attack leak detector. So the idea is, when you design a chip, one of the problems is you see a leak, the side-channel attack is successful, but then you don't know where it comes from, and you cannot inform and help chip designer on what they should look at and where countermeasures should be applied to prevent the attack. So a leak detector ideally will tell you, hey, this is line blah, or if you have an FPGA, this is this part of your block that you need to fix. And I have a full talk on that I did, I think, last year at DEF CON and Black Hat. So if you'd like to have more detail, please go check out the slide and the video. But very briefly, the way that works, and that's for illustrating the idea of reusing deep learning tools in a creative way, is this idea that in deep learning, there is this tool called explainability. It's actually an entire field of, can we explain what the model is seeing, because models are hard to debug, and people need to get confident that what the model have learned is really a generalization of the concept and not what they called surface statistics. An example of that very early in the machine learning community was, there was this data set, and at the bottom of every horse image, there was a kind of a copyright on the bottom right. And so the model, instead of learning to recognize horses, used to recognize the text. And of course, that's really, really bad, because then the performance of the model are not representative of its ability to generalize, but instead its ability to recognize text, which is not what you want. So to avoid these errors and try to do quality control and understanding what the model is understanding or not, they come up with this field of explainability. And here is a brief example of how that would work. So you'll have a model, and then you would apply explainability, which most often use inverting the gradient. So you put your model and you look at how the gradient is going, and you feed it an image, here cat and dog image, and the model will say, and ask for a given class he did predict, how it can to predict that class. So here we have, okay, there's a boxer. How did he come up with that decision? And the answer you're going to get this kind of a debug image, which say, well, I did look at the face, and here's where I looked at, where is my attention went. And you look at it as a human, and you're like, okay, that's reasonable. Looking at the face is what I expect you to do. That's okay. And then you say, okay, the other thing you predicted was a tiger cat. How do you come up with that conclusion? And here, the model will show you a region which is mostly fur and stripe. And that's where you're like, oh, that's probably not a good thing, because cats have fur with stripe, but also tiger and other animals. So probably not what you wanted. And so that's a little bit more concerning. Doesn't mean the model is broken, but it just means that in this specific case, it went for the easiest way, which is like, hey, in my data set, most likely there was only cat with this type of stripe, and he anchored to that surface statistics instead of recognizing the face and so forth. So that's a bit of a problem, and your model is probably not as good as you hoped. So we did the same for power traces using a leakage map where we would try to isolate very precisely, as you can see on the slide, exactly which part of the trace were responsible for the model being able to break or to recover the bytes. And we had to adapt the technique. Obviously, this is not the standard one, because the standard one I'm more concerned about, as you see, diffuse map, where we're really concerned about having a single point. And the reason why this is important is because if you use standard technique, and the way we would test that is we would take the top 4 more important points in the trace and remove them and see how far the accuracy drop. And you can see that for byte 7, like for example, with activation map or GradCam, which is very, very known techniques, the model doesn't drop accuracy. This is not good enough. So we went back and we worked on a different technique, inspired of course by previous work, but kind of specialized for us, and that would give us, you see, way better decrease in accuracy, meaning that the point we are flagging as important are the points who really contribute to the decision, which is exactly what we want. And so if you combine that with a lot of other tools that I don't have time to cover, such as our CPU emulator, which allows us to go back from a point in the trace to the exact instruction being used, you can combine all multiple traces, multiple explainability, and lo and behold, if you apply it to TinyAS, you find that most of the leakage comes from line 213, and 213 is exactly where you have sub-byte in and sub-byte out, which, if you remember the beginning of the talk, is what we try to attack. So we are able to go full circle from attacking with deep learning and back to the model telling you what he found and how it did, where it found, what it exploited into the algorithm, and they match. So it gave us great confidence that it is possible to use deep learning explainability to find leakage into such an attack, which is very important in the future as we develop better defense, to be able to help developer, chip designer and implementation designer to quickly figure out what is the main problem as of now in the implementation. So there are many, many other ways I think we can exploit or we can use the deep learning tools and hardware to go faster. So the obvious one is using the hardware developed for deep learning for cryptanalysis. Those are hardware very, very good at doing multiplication and tensor addition and so forth, so very, very fast. So that will help us. However, what I would contend is we can go deeper and we can decide to use some of the library which are built on top of this hardware. TensorFlow, JAX come to mind. And you can write your algorithm that way, and that gives you a lot of benefit. It helps you to distribute your computation very easily, because those by nature, those libraries are meant to be distributed on multiple hosts, multiple CPU, multiple GPU. And so it's also, they are very, very well used, very, very optimized to do what we call polyhedral optimization and other type of optimization on tensor, which makes your computation faster. So you get hardware accelerated, optimized, distributed code, and you can write it in Python if we were to use those libraries. So for me, there is like here a interesting place where learning deep learning library, even for cryptanalysis, is beneficial, because you might be able to do cryptanalysis implementation, which are way more efficient and with a lower effort and better result. So takeaway of this talk. First, there are natural fit for deep learning applied to cryptanalysis. Side channel come to mind. This is probably the most obvious and the most active field today, because of the statistical nature of the problem and the fact that you have a lot of data. That is bringing a whole new world of interesting challenges to overcome, which is making implementation resilient to those better attacks. And now that as the scale is tipping into the favor of the attacker even more strongly, how do we counterbalance that? So there is a lot of research there as well. And as I mentioned, there's a lot of exciting area where I think there's a lot of potential for breakthrough, and yes, AI will be helping us. So if I have to conclude and answer my own question, does deep cryptanalysis a fashion or revolution? I truly believe it's going to be a revolution. It's going to change how we do the field. Not all of it, not everything is suitable for it, but however, there is quite a big chunk of cryptanalysis problems which are amenable to deep learning, and those are going to really benefit from the advance of deep learning. And by bringing them in to our field, we will be able to make incredible progress, I think, in the next 5 years. And with the field starting to be figured out, there is a lot of opportunity. So if you're interested in doing research in the space, that's a really great time to start engaging in it and join our small but growing community. Or at least follow along, right? And try to, if you're interested in cryptanalysis, that's really the place where you want to keep an eye on, because I'm pretty sure a lot of good results are going to come out from many groups who are starting to work on that space. Thank you so much for having me. As usual, if you have any question, please let me know over social network or by email. I'm always happy to answer any question. And I hope this talk have gave you a overview of where we are and get you excited to join us and do more research in the space. Thank you so much.